Hello, my dear students. Warm welcome to all of you. We are with physics now. Okay, we'll be talking very seriously about physics now. Okay, myself is Dr. Shobboshachi Shen. I'll be offering you the physics courses, course objective, course outcome. You can see on the screen, and we are in outcome-based education. So every course is mapped with what is its probable outcomes, which I have illustrated later on. Now there are five modules. Now we'll be going adapting one by one to each module and explore the world of physics. Now let us explore what is the topic of the day. You should keep one thing in mind, that whatever we teach in these classes, each video lecture is basically a building block of your future engineering courses. Each class is going to give you some fundamentals, some new concept. And if you add all those concepts at the end of the semester, you will get the correct path of entering into your own engineering curriculum, because all your curriculum are essentially the application of physics. Engineering means physics applications. So let us explore it a bit more. Thank you.
Class there I illustrated that is what we should do in this class. It's a class of what we do in this class, and I possibly frustrated you with the answer. In this class we'll be talking a bit of physics. We'll do physics, we'll think physics, we'll sleep with physics, we'll dream with physics, because you are learning engineering, and whatsoever with the engineering stream you have chosen, these are all physics. These are all physics-based streams. It may be electrical engineering, application of your the ideas of electricity, magnetism, current electricity, all these things will be applied there. It may be mechanical engineering. The first thing you learned in physics was mechanics. Okay, so it started with the three laws of Newton. Okay, and you are experts of solving hundreds of problems while preparing for joint entrance examination. And at that time world was mechanical. You solve this frictional problem, rotational problem, somebody under gravity, a fluid is flowing, the concept of viscosity, surface tension, general properties of matter, we call in physics. So these are all mechanics problem. Okay, even the kinetic theory of gas molecules moving in a container, it's at the end of the day, it's a mechanics problem. Okay, and in mechanical engineering, you'll apply those senses again. It may be the latest of the devices, semiconductors. You studied a bit of diodes, transistors, logic gates. Okay, and that is a part of physics that you have learned, and that will be applied in your digital electronics classes. And they are that those logic gates are the fundamentals, are the building blocks of your computer architectures. Okay, so the students of CSE and IT, your hardware part, okay, how it will work, how it will be designing. In digital circuits, you learned about the zeros and ones. Zero means low voltage, one means high voltage. So how do you make zero state or one state? Okay, so all these have got a physics origin, because you have to realize those zeros and ones through some voltage values in an electronic circuitry. For example, if you use two diodes, you can make a OR gate. If you use a transistor, you can make a NOT gate. So there physics lies. Okay, how they could operate. So that will be the application of the physical sciences. And CSE and IT students, for you, there is a very good news, is that the latest computation has come up. Okay, and it is based on one of the basic principles of physics, that is called quantum computation. Okay, you'll be learning a lot of quantum mechanics in first year, quantum mechanics 1, in second year, quantum mechanics 2, as I was showing you in my first video lecture. Okay, because why it is so important? Because it is the language of learning modern physics. If you have to explain how electron moves in a semiconductor, you have to explain it with the ideas of quantum mechanics. If you have to explain how a car moves, bus moves, train moves, how Virat Kohli powers his bat, how Dhoni hits a six, that all those things can be explained with the Newtonian idea, classical physics concept we call. What is classical, what is modern, all these things will come in my classes. But if you have to describe electrons in a metal, electrons moving in a semiconductor, electron moving in a diode, electron moving in a transistor, all these electronic stories are explained in the language of quantum mechanics. And quantum mechanics have got something very good to offer for you. The latest computation, quantum computation. Okay, the Google has come up with quantum computer last year, you should possibly be knowing. So it is a so as now in 2020, okay, as a computer science student, whatever you will be learning, and when you will come out in 2024, okay, you will be ready to take up the challenges of the latest computation, quantum computation. In physics course, you will come to know the ABCDs of this quantum computation. It may be biomedical engineering. Okay, it's biomedical engineering. You have to work. You have to be working in the medical sector, where suppose you have to know what is X-ray, how X-ray is normal X-ray, we call 2D X-ray, is different from CT scan, where we also use X-ray, how X-ray is produced, what is ultrasonography, how ultrasound is produced. These are all coming with physics origin. Or even the latest, suppose you as a biomedical engineer, you have got a lot of societal role to play. You'll be placed in hospitals. Suppose say cancer patient is undergoing radiation therapy. Okay, there 6 mega electron volt photon hits the cancerous cell and kills the cancerous cell. So what is a 6 mega electron volt photon? How to produce it? How to design it? You see, in hospitals there's a physics room for that. So your physics concept is needed there. So whatever you do, it may be the computations, this computer science and IT, it may be the hardware part and the latest computation. It may be our own electronics, our own electrical, mechanical, civil, biomedical, whatever you learn in engineering courses here in this college, all are physics. It's all physics. Your spectacle is physics. Your brain is physics. Your hand is physics. Your thinking is physics. And if you know physics, you will become, okay, and you add a bit of mathematics with it, okay, you'll become a wonderful engineer. Okay, so that's why knowing physics is very important. Okay, here in our courses, in this first year physics course and second year physics courses, as I mentioned in my lecture one also, we'll be mainly offering, okay, we'll mainly make framing the fundamentals of whatever you'll be learning in your future classes. Now, if you miss fundamentals, what is going to happen? I have told you last day. So now today I will get into my business. I will be talking into the first topic of my discussion. Okay, the prerequisite of this course, as you can see, there is a course code PH 101. It is called Physics 1. Physics 1, as I mentioned in my first video lecture for your class, that it's a very general course. Okay, every students have to undergo this, and physics 2 is more stream specific. We will discuss that in right time, not now. Okay, and to learn this, you need to know some fundamentals of your 10 plus 2 level of knowledge also. We'll brush up those knowledge as the time goes on. Okay, so I'll begin my discussion, begin my journey. You see, if you look at your syllabus, there are a few modules. Okay, there are a few modules. Okay, the the modules are like this much. Okay, there are a few modules. Okay, the modules are, it may be the waves and oscillation, okay, which is everywhere used. The concept you will come to know. It may be the physical optics, interference and diffraction, and it may be the basic idea of solids, okay, how it is made up. It may be modern optics, the lasers and fiber optics. So these are something fundamental which everybody has to know. But and the most modern topics in this course is quantum mechanics. So we begin with quantum mechanics because it is the language of learning modern physics, as I mentioned. Okay, now this is me. You can contact me. Okay, all my contacts are provided there, as you could see. Okay, so you just get in my touch. Any problem, I'll be there to help you. Now, this, you see, every course that you are learning in this college, okay, as I, again, it is connected with my first lecture also, but I'll remind you, every course, you are in a outcome based education system. It is popularly called India in 2015 signed Washington Accord, that according to that, all the engineering colleges in India should have similar syllabus. Okay, and the essence of that is that we have to follow a definite curriculum that is followed by designed by ICT. We are following that, so that has got some prescription. Okay, and there are some at for all our engineering programs in our college. Okay, they need some accolades. Okay, some quality assurances. Okay, these are maybe very hard word to hear in in these early days of the class. But I want to tell you, whatever you are learning in these courses, some of your friends learning in some other institutes, maybe the top premier institutes like even IITs or JUs or any other premier institute, their structure, their curriculum, the what amount, the type of course that they will undergo in their course is also very similar. The main idea is that at the end of the day, when you come out after 4 years, you should have certain attributes. Okay, they are called graduate attributes or program outcome. If you're learning computer science and engineering, or if you're learning information technology, when you pass out, you should have some qualities as an engineer. Okay, that is already defined. Okay, and they are called program outcome of your own program, maybe CSC, maybe IT, maybe mechanical, maybe civil, whatever you choose, whatever you are learning. Now, they're very similar. Okay, for example, the first one is that you should have some you should have ability of solving complex problem with the ideas of science and mathematics. So what I'm doing science here, physics here. So similarly, uh, that means to achieve that goal, you have got your physics course here. So our course, whatever I offer, whatever we teach, has got certain outcome, which is giving you the attribute you need as an engineer. They are called course outcome. And also this course we are offering, because that has got some objective also. Objective means what I have to tell you, what I am going to teach you in these courses. Now, the main objective of this course, as you can see there in the screen, this course objectives are very clear. This is going to give you, will be giving, I'll be, as I mentioned, whatever you learn are all applications of physics. So we have to get fundamentals very clear. Okay, the basic ideas of physical sciences will provide. You have to apply them in practical classes. Okay, you've got your own projects, so they apply. Okay, and at the end of the day, physics is all thinking. You will try to gear up, open up your mindset through variety of courses you are having. Okay, so that you get some innovative mindset, and as an engineer you can prosper. But basically, fundamentally, my job is to tell you the fundamentals of whatever you'll be learning in your own engineering courses. And it is expected, as I was mentioning, this course will give you some attribute, some quality, some from they are called course outcome. Okay, so after undergoing those course, you'll be obviously able to explain the basics of what is lasers. Laser is a light at the end of the day, but how it is different, how it is special, what is optical fiber, what are semiconductors. Okay, okay, and the basic optical phenomena like interference, etc. And you'll be able to analyze the crystallographic structure, that is the basics of semiconductors. Okay, and you'll also realize why quantum mechanics is so important in your life now, which was not present at all in your earlier life. But the moment you have chosen our college and the engineer and the courses we are offering, which are very potent, very modern, and which needs one of the most modern physics application, that is quantum mechanics. So you'll realize this after undergoing these courses, and that will be making you able to solve the complex problems of your engineering needs if you have these qualities. Okay, if you have the fundamentals, then you can apply it. If you know why, if you develop the analysis power I'm talking about, then it will be help. You'll be successful in your own engineering domain also. Okay, because there you have to use science, you have to do analysis, you have to do application of the science knowledge in your engineering program, analyze it, evaluate it, and ultimately create something for our human society. And that is your major role as an engineer. So a lot of responsibilities waiting for you. Okay, this is called COPO mapping. I'm just you can see whatever I am talking you. It is just presented there in a quantifiable manner. Now look at this person. He's a very famous person. Do you know his name? His name is Max Planck. His famous Planck constant, and he is regarded as the father of quantum mechanics or father of modern physics. What Planck did, he did a magic in the year 1900. What is that magic? He explained blackbody radiation experiment. Now you may wonder what is the magic in it. Magic is that blackbody radiation experiment is an experiment of thermodynamics. It's thermal physics, I should say. Then how quantum mechanics comes into business? That is automatic question. You know, any new physics concept cannot automatically can drop from sky. Okay, it has to have some origin. You see, the Planck in the year 1900 actually explained blackbody radiation. So that let me talk to this story a bit. And at that time, part of history of physics or physical sciences was dominated mainly by classical persons. Okay, Maxwell was there with his electromagnetic theory. Maxwell was there to explain the motions of molecules of gas in a container. The same Maxwell will be having very good relationship with you in your AM theory classes with his laws that tells you how radiation goes through passes through a medium. But he has also expertise in explaining the thermodynamics part of the life, also the kinetic theory of gas, how gas molecules moves in a container. So all those ideas was given. So it was dominated mainly by the class theoretical physicists or the thermodynamics people. So one experiment with black body was going on. And what happened? There was some crisis with that experiment. And Planck, Max Planck, this person, the god of modern physics, the father of modern physics, okay, he explained with a wonderful concept which was beyond imagination at that time. So what Planck did, okay, you have to know that. So basically, as I mentioned in your first discussion also, this entire study of quantum mechanics one, or this quantum mechanics one you are learning, okay, that you'll be learning quantum mechanics in two steps. In first year, we'll be talking a bit of theory, that is called quantum mechanics 1. Theory means how everything developed theoretically. So I'll talk about some experiments that was carried out between 1900 to 1927. Now, from 1900 to 1997, I'll talk about few experiments, and these are so wonderful and crucial years in the history of physics. Is that each experiment at the end of the day is going to give you one new concept. Now, which new concept it it gives, that will come to know at the end of the day. Okay, so this is called theoretical development of quantum mechanics. Okay, or quantum physics one. In first year, we'll develop that theory. So we'll learn each experiment. It, okay, we'll learn each experiment, and at the end of the course, at the end of the semester, we are supposed to have some new concept, a little bit of new idea. So each experiment will slowly develop some new concept, or I should say some deviation of the way you have been looking at the physical science, or if you what physics does, it actually gives you the spectacle of looking into the outside world. So your spectacle, your vision will be slightly changing, okay, the moment you cross 1900. Okay, 27 years, vision will be changed. So what I shall do at the end, I'll be talking about each experiment, and at the end of each experiment, I'll tell you what you learned extra out of that experiment, how it deviates your classical concept or your old concept or your the physics you know. At the end of that semester, or at the end of all these lectures, okay, in some new concepts will be jotted down. Now you should keep them inside your bank account, in your vault. You should keep all of them in our pocket. Why? Because next year you have got a physics 2 course where you have to learn quantum mechanics 2, where these theories will be all applied. So first year is all development of concept. Okay. Second year you have to apply this physics to this quantum ideas in the problem of explaining how semiconductor acts, in explaining how electron moves in a metal, explaining how electron moves across the junction of a diode. So all these are quantum mechanical phenomena. Okay. So all these things application will be done in the next year courses. So now let us develop the theory. And as mentioned, it all started with Max Planck. Planck explained black body radiation. So what Planck did, so let us get to know. So it's all theory now. So it's all experimental discussion now. Okay, so what Planck did, let us get to know. Now, this is what Planck did. Planck explained black body radiation. Okay, now look at these pictures. What I'm doing now, I'm doing a giving a twist in the story. I will first explain to talk about what Planck did. Okay, it's not a matter of a single day. What Planck did first to realize what is the change he is making in the development of in the history of physics. So you have to realize that. You have to understand that. Okay, then and only then you can understand the contribution of Planck. So what shall I do? First, I will explain you this in the experiment of black body radiation. This total experiment of black body radiation is not our objective to learn. Our objective is to learn the idea that is given by Planck for the development of quantum mechanics or quantum physics. But I'll talk about this experiment of black body radiation because that will tell you how everything is actually coming up. You know, to talk about black body, first thing you need to know, you possibly we have possibly heard about what is called a black body. Black body radiation, okay, is the full word I am using. You see, so to learn this, so you see there are two words are connected: black body and radiation. So black body means some kind of body, and what does it mean by radiation? So now let us first explore what is called a radiation. Radiation means it's a kind of a wave. Now concept is a wave means what is wave is. So to answer this question, wave is a disturbance. You see this slide that I am showing on the screen, it's a very important slide. Okay. It's a very important slide. Okay. This is giving you some basic knowledge of what a wave is. Now you should keep this idea in mind. It will be utilized many times in my class. Okay. Wave means disturbance. Wave means variation. Wave means fluctuation. Wave means some change. Okay. So you see something is fluctuating. So these are all waves. Now the wave may be a sound wave, audio wave or acoustic wave. It is created by the vibration of matter. You see, the tuning fork is vibrating and sound is created. Or if you clap your hand, you see I'm creating sound. Okay, who is creating the sound? My hands are creating the sound. Okay, see, my hands are creating. So who makes the wave? My hands are making the wave. What my hands are? My hands are matters. So matters are vibrating. Matter itself is changing. Material particle itself is changing. That is called a wave. Or even you can see the case of spring vibration also. Okay, so first matter has to vibrate. Material particle has to vibrate. And if my hand is vibrating, the air here gets compressed also. Okay, compressed and rarefied. Okay, or the tuning fork is vibrating, air in front is also compressed and rarefied. By the way, sound wave is passing through the medium. Sorry. Now you can realize it. Okay, so it's a vibration of matter. Another wave may be electric wave. Electric wave means a signal. Okay, DCAC, you can see the difference. Wave means disturbance. Who is vibrating in case of AC? Alternating voltage or alternating current against time. Or it may be the alternating magnetic field. Okay, you can see magnetic field is changing. So who is vibrating? The magnetic field is vibrating or magnetic flux is changing. You can see there phi. Okay. Now mixture of electric and magnetic field is called an electromagnetic wave. You can see it is propagating along some direction, say X in my picture. So you may give it is actually represented by some vector called wave vector. But what is most important, you see the red and blue line. Along the blue line, electric field is changing, and perpendicular to that, B is the magnetic field changing. So here it's a wave of both electric field because electric field is waving. Waving means changing, and magnetic field is also waving. So magnetic field is also changing. So it is called an electromagnetic wave. Okay. And an electromagnetic wave is also called a radiation. Our favorite light wave is also an electromagnetic wave, X-ray is an electromagnetic wave. Gamma ray is an electromagnetic wave. Is an electromagnetic wave. The heat wave is an electromagnetic wave. All are electromagnetic wave. What is the difference? Difference is in their wavelength. You see the picture. The wavelength is there. You see the screen here. Okay. You see the wavelength here. You see this is a visible spectrum, or visible light means the 7 colors. The wavelength of red light is close to 6,000 angstrom, sorry, or 7 8 close to 8,000 angstrom I am choosing, and the wavelength of violet light may be like 4,000 angstrom. So 4,000 angstrom to 8,008, and 1 angstrom means 10 to the power minus 10 meter. So 4,000 angstrom to 8,000 angstrom means the wavelength of visible light is thousands of angstrom. Okay. Now X-ray, gamma ray, their wavelength is much smaller. Okay, 0.1 nanometer means like one nanometer means 10 to the power minus 9. So that means it is like 1 angstrom. Okay, and gamma ray is even more lesser. Okay, you can see there. And you can see there also the left hand side, the radio waves, the millimeter wave, heat waves. The heat waves wavelength is very high, so their energy is very low because of the formula is equal to hc by lambda. Lambda very high means so energy is less. So that's why greenhouse effect takes place. Heat comes inside maybe is, you see inside, it cannot go out because its energy is very less. That is the origin of the greenhouse effect. Okay. So all these are radiation. So by the word, all these are called electromagnetic waves. So electromagnetic wave is a very broad concept. It's a mixture of electric field and magnetic field simultaneously. Our own light, favorite light, is an electromagnetic wave. Okay, and the wavelength of that light, electromagnetic wave light, okay, the visible spectrum is like 4,000 to 8,000 angstrom. So this is the part of the entire electromagnetic spectrum which you define that as visible light. But just below that there is infrared light whose wavelength is the wavelength is slightly above red is infrared. Okay, suppose if you have got this remote. Okay, if you use this remote and if you have to switch on a TV, what should happen? So from here, okay, from here you can see there. You look at the remote, you can see there. Okay, just in front of the remote, you see there is a light. Okay, there's a source. There's a source of radiation. This is an infrared source. So if you have to operate the TV, I'll switch on the button. But do you see a signal is going from the remote, from this source of the radiation to the TV? No, it can't be seen because it is not in the visible spectrum. But the signal is going. Our habit is to change the channel continuously. So I will press the button, each time signal will move there. Okay. So basically, this is not supported by our naked eyes. So you do not call it a visible light. It is not visible to us, but it is there. It is called infrared light. Wavelength is slightly above 8,000 angstrom, maybe 10,000 angstrom or something. In the hot summer, you see, it is suggested that you should not go to the sun in the month of April, May. Okay, why? Around 2 o'clock, it's very hot summer. Okay, why? Or if you go to the sun, you put SPF 40, 50, 60, 70 on your skin. Why? To protect your skin from ultraviolet radiation of the sun. But do you at all see a violet light is coming and hitting your skin? Never. Because it can't be seen. That is called an ultraviolet light, whose wavelength is slightly lesser than the violet light. So there are many more radiations which you can't see. You can only see very little portion, 4,000 to 8,000 angstrom. Okay, X-rays having smaller lambda compared to visible light, much smaller lambda, 1,000 times smaller lambda, and heat waves, they have got much higher lambda. Okay, so their energy is much lesser. So when I talk radiation, I talk about all of them. Okay, so now let me get into the business more. Now, what is called a black body? Now, the definition of black body I have written there. You can see there. A black body is a body which can absorb any radiation of any wavelength completely incident upon it at a low temperature. Suppose this object, you can see here, is it a black body? It is black though, it's in color. Is it a black body? Answer is that it can be a black body. First thing is that I have to keep it at a given temperature. What is the temperature of this body? The room temperature. Now at this temperature I can call it black if any radiation coming in get fully absorbed. Then what is the meaning of full absorption? Full absorption means suppose a radiation on a surface, radiation is coming in. If 100 unit radiation comes in, a portion gets reflected, a portion gets absorbed, and a portion gets transmitted. Suppose out of 100, 80%, normally 80% is reflected, and 20, suppose because it's a solid body, so there is no transmission. Suppose 80% reflected, 20% absorbed. So then we say is the absorption ability or absorptivity is 20%, reflection ability or reflectivity is 80%. But I cannot call it a black body. Definition is that if any radiation is coming in, 100 unit of radiation coming in, the full 100 will be absorbed by it, no reflection. So absorption ability is 100%. So and it should have no selection rule. Any red light coming in, fully absorbed. Blue light coming in, fully absorbed. Green light coming in, fully absorbed. Pink light violet light coming in, fully absorbed. X-ray coming in, fully absorbed. Not selection rule. So any radiation of any wavelength coming in, fully absorbed. But if you don't understand, suppose you see, look at this red pen. You see why it is red. So if radiation coming in, it is absorbing all color excepting red. So it has got a selection rule. It is only absorbing all colors excepting red. But if this has to be a black body, it has to absorb all radiation, no selection rule. Surface may be appearing to be darker, blackish, but it is black because not of the color, because of this ability of absorption. No selection rule. Whosoever, everybody is welcome kind of thing. Any radiation coming in will be fully absorbed. Okay. Now, if the other part of the story which is written in violet there, if I hit it, then what would happen? Suppose I hit it. Okay, I hit it. If I hit it, I cannot hold it. Okay, I have to throw it away. Why? Because it will be hot. So if I hit a body, it will emit heat waves. So that is the message is that if you hit an object, it will emit radiation and fundamentally emit high wavelength radiation or low energy radiation, heat waves. Just imagine an iron rod. If you make it hot, if you imagine an iron rod, if you make it hot, what would happen? Okay, first it will become hot. Suppose you are putting the iron rod in the fire. Okay, it cannot hold it after some time. Why? Because it will become hot. So it is emitting heat waves. Message is clear. If you hit a body, it emits radiation. If you hit it further, it will become reddish. So it is now going to a little bit smaller lambdas compared to heat waves. Okay, red light is coming, but it's not a black body. Now, if you hit it more, it will be white hot. Again, I cannot call it a black body. Maybe I can call it black if it emits all types of lambdas. A red hot iron is not a black body. A white hot iron rod is not a black body. A body will be called black at a high temperature because of heating. If it emits all types of radiation, you can imagine 0 to infinity theoretically, practically from very small to very large number of wavelengths. Okay, so this is the message. Okay, then you may ask me, who is that source? Has got that power of absorbing everything and emitting everything? Answer is that ideally if it is a black body at a low temperature, it will absorb any radiation of any wavelength fully. So ability of absorption should be 100% ideal. And if I hit it at a high temperature, it will emit all radiations possible. So ability of emission, or you call it emissivity, is also 100%. But the word ideal is used for something which is impractical. Okay. So what is a black body in practice? Practically, a black body has to emit radiation not from 0 to infinity, but from very low wavelength to very high wavelength. Okay, and absorption also may not reach 100% absorptivity. Maybe getting very close to it. Okay, 99.9% or so. Okay, now our objective is not to learn the details of the black bodies. Our objective is to learn experiment with black bodies. So obviously now we have to talk about the experiment with black body. Now the point is that if you have to deal with an experiment, you have to be practical. Okay, so now I have to present how a black body in practice look like. Now this is a black body in practice. Okay, if you look at the black body in here it is. Please see the picture. It is basically a hollow enclosure. I put a 2D view, but it's a 3-dimensional box. Okay, it's a 3D box. You see this box has got some outer wall. These are the outer walls, and this with green arrow I mark the inner walls of the box, or these inner walls of the cavity. It's a hollow cavity, much like your classroom. Your classroom is like a 3-dimensional box. Okay, suppose Classroom is occupied by teacher, student, chair, table, etc. And suppose nothing is there, so it becomes an empty box. Okay, so like that, it's an empty box. The inner walls of your classroom are all coated with light color. Okay, why? Because of better reflection. Here the inner walls of this cavity are coated with all dark color, black color, coated with lamp black. Why? Because I want better absorption. Absorption, it is coated with lamp black because ability of a lamp black absorption ability is 95 to 98%. Now, suppose a radiation is coming in. Okay, that blue arrow, I do not know whether you can see it or not. Let's try to identify. This is a blue arrow, radiation of intensity I1 coming in. It is incident on a black surface. So what would happen? 98% of this incident I1 will be gone and be absorbed inside the cavity. Only 2% will be reflected. Okay, by the following the law of reflection. Okay, that is the I2. Now I2 is incident on another black surface on the right side. Here it is incident on the right side. So only 2% of I2 will be reflected, remaining 98% will be absorbed by the black surface. So if there is I3, I3 is just 2% of I2. And you can realize I3 is less than I2 and much less than I1. So where the radiations are going is being absorbed by the cavity. So now it is incident on another black surface, and 98% of I3 will be absorbed, only 2% will be reflected. If it is I4, it is 2% of I3, only much lesser compared to initial I1. So black surface is absorbing. Now if the I4 is reflected and incident on another black surface, 98% of I4 will be absorbed, only 2% will be reflected. I call it I5. I5 will be again will lead to will be again incident on another black surface. 98% of I5 will be absorbed and reflected intensity will be I6, which is much lesser compared to initial intensity. So each incident means huge absorption. Who is absorbing? The black body, the surface, the inert surfaces of the inner walls of the cavity is absorbing the radiation. So as a result, almost entire radiation is getting enclosed inside the cavity. Okay, so you get huge very high ability of absorption, and because you see it's a multiple reflection process, it will be on and on and on and on. So each incident means huge absorption, and ultimately ends almost entire I1 gets absorbed, but there will be some practical loss if any radiation follows that red line. You see that hole you have to keep, that is called an orifice, because through that hole radiation is coming in. You have to keep a hole there. Okay, but that is also detrimental here. Through that hole, if there will be any radiation reflected towards that direction is a loss. To avoid that loss, minimize that loss, not to avoid. Okay, the size of the orifice is very small. Okay, you have to keep a hole because if you hit the body, the second part of the definition, radiation has to go out. So how it will go out? Okay, it will go out. Otherwise, there will be huge accident. Okay, if you do not give radiation, uh, no space for radiation to go out of the body when you are hitting it. Okay, in the second part of the definition of black body. So the idea is that if you hit it, okay, radiation will go out of the box. Okay, okay, but to avoid that, to minimize that loss, not avoid, to reduce the loss, okay, you have to make the size of the orifice as small as possible. So you can get very high absorption, but this practical loss will lead to very absorption ability close to 99.99%. Okay, so this is a black body in practice. So now this black body may be at some say room temperature, it is black because of its ability of absorption. But the actual experiment with black body was done with the heating. Okay, so it is now at a low temperature. You see the picture, beautiful animation is there, radiation is there and getting enclosed inside the cavity. Whatever I have been telling you, it is shown with with an animation there. You can see it. You see that is iron rod. Now look at the bulb. Okay, it's beautiful. You see, you are hitting it, you are hitting an iron rod, it is becoming reddish. That's something I was telling you a few minutes back. So if you hit a body, it will emit radiation, but I can call it black if it emits all types of radiation. Then and only then it's a black body. That filament bulb maybe a practical black body. Sun, the source of all radiation, is a black body because of the second part of the definition, because of heating. So left hand side of the picture is a black body definition at a low temperature because of absorption. It's a black body, and right hand side of the picture is basically it is black because of the second part of the definition of the black body, heating. That filament bulb is a practical example is of regarding there is a black body. You'll be doing some experiment in lab. You'll be determining the constant of Planck. You'll be determining the constant of Stefan. You'll be doing an experiment with solar cell. All these things we'll do. So there will be regarding the a filament bulb is like a black body. Okay. So now let me now talk about the heating of the body. One message you have got: if you hit it, it is going to emit radiation. But I can only call it black if it emits all radiation. Red hot iron is not black because it is only emitting red light or remaining a smaller wavelength. But I'll call it black if it is emitting everything. Keep this mantra in mind and move forward. So I've taken a black body. Now I've heated it. Okay, see what is going to happen. If you hit it, low temperature to high temperature, it is heated. So now you see the beautiful pictures are there. I have heated it at various temperature: 900 degree Kelvin, 750 degree Kelvin, 3200 degree Kelvin, 1500, 5500 degree Kelvin. Question is that are they black? Answer is that I can call it black if you get this much. Okay, if it emits all types of radiation, then and only then I can call it a black body. Okay. So now here at this juncture, I'll be talking about the experiment. Suppose I have heated the black body from low temperature to high temperature, from some temperature maybe T1 to T2. T1 maybe say 300 degree Kelvin, T2 maybe say 1300 degree Kelvin. So at 1300 degree Kelvin, it is making the emission of all theoretically very small to very large number of wavelengths coming out of the box. So what would happen? Okay, you will the radiation is going out. Now at this juncture, one experiment was done. Okay, there is an experiment was done using bolometer. Okay, bolometer, what was done? This emitted radiation was passed through a fluorescence prism. What prism does, it will disperse the light. So dispersion means you will get that white light, or sorry, that white light in a sense that it's all types of radiations are going out. Okay, so all the radiation going out through after passing through the fluorescence prism, it will be getting into pieces, into components. So what was done using bolometer? Okay, there is a galvanometer kind of arrangement. So using that, you can measure the intensity corresponding. You measure the current actually corresponding to each and every light. Okay, just in making it on a photo detector. So for every as the depending on the wavelength, for each wavelength, you measure the corresponding intensity. Actually, the corresponding current was measured. Okay, using bolometer. So what it does is gives you the value of intensity or energy corresponding to each and every wavelength, and that was recorded and it was plotted in a graph. Okay, energy. Okay, this Levitian radiation passes through the fluorescence prism, gets into components. I am not showing you the entire detailed experimental details, not needed, because we are happy in knowing how Planck explained the experimental results. Okay, so for energy corresponding to each and every lambda was measured, and now it is plotted. So how do you plot it? You get a, you see after if you do the measurement, you get a data table like this. So for lambda, you see all the wavelengths are coming out. Lambda 1 may be 20 angstrom, lambda 2 may be 200 angstrom, lambda 3 may be 3000 angstrom, lambda 4 may be 500 angstrom, whatever it may be. All lambdas are getting out. Using bolometer, theoretically 0 to infinity, practically very small to very large lambdas are out. For every lambda, you measured the energy, like E1, E2, E3, 45. So you have got a data table. So your next job is to plot it. If you plot it, you will get a beautiful graph like this. If you look at the graph, this graph has got few portions. Okay, you see for small lambda, for small wavelength, the graph initially grows up. For high lambda, the graph falls down. Okay, you can see here. You please see. This is a region. This is a region. You see here, these portions I am talking about. Here, if you increase lambda in this region, if you increase the lambda, increase the wavelength, what will happen? You can see the intensity is also increasing. With the rise in lambda, it is increasing. And for this region, if you increase lambda, you can see the energy is decreasing. So there is a dual nature. As a result of that, in between it is passing through a maxima. Now the wavelength at which you are getting the maxima, okay, okay, I now call it say lambda max. Okay, suppose the body temperature is T1 to T2, so I call it say lambda M2, and this kind of thing. So now this is a peculiar graph. This is the experimental graph of black body radiation. So now I'll talk. Our next focus is to talk about this graph a bit more. So what was done by this team? Okay, of the people working on black body radiation, they have further enhanced the temperature of the black body. You see, it was at T1, it is heated to T2. You get that graph. Now it is heated further to the temperature, say T3. If you heat it at a higher temperature, now you notice the energy you obtain is slightly higher. Okay, it is E1A, it is E2A, it is E3A. So slightly higher energies, higher or lower, you God knows. Okay, E4A. So now whatever for, so again for every lambda, you get a corresponding energy. And now again you plot it. And if you plot it, suppose initial temperature was say 1750 degree Kelvin. Suppose this is T2. Now it is heated to a higher temperature, maybe 2000 degree Kelvin. Suppose this is T3. So now the at T3, you get this violet graph. So what you notice, you see both the graphs are very similar. Initially, it increases with lambda, and finally it decreases with lambda, and in between passes through maxima. Now, can you notice what is the difference between the two graphs? Two differences are there. They're very similar in look. Okay, the first difference is that you see at a given wavelength, say at this point, at a given wavelength, okay, say for this wavelength, we may call it say lambda 1. For lambda 1, you notice the energy corresponding to the corresponding to lower temperature is lesser compared to that of the higher temperature. So that means at a high temperature at T3, you are getting more energy compared to the in the case of T2. So the idea is that these E1A values are getting higher compared to the that energy that we obtain at a lower temperature. So that is the first observation. Second observation is that you see in the higher temperature, you are reaching maximum more quickly. In this case, in the first case, this was your maximum value, lambda maxima. Now, in the second case, what you are doing, you see in the second case, this is the value of your lambda maxima. So you are reaching lambda maxima is a bit quickly. Okay, if you rise the temperature, is a very important observation. The two observation, at a high temperature, energy emitted is more, and at a high temperature, you reach maxima more quickly. Or okay. So now, if I just consider another case, suppose you it is heated more, T1 to T2 to T3 now to T4, and this is your data table. Now I consider again same old story. For every energy, the every wavelength energy was measured, and these are the energy values. It was plotted. If you look at the plot, the graph obtained is something like this much. This is the graph obtained. Very similar graph, you can see. And only difference is again very similar graph. Small lambda it grows up, high lambda it falls down. And again, if you compare the graphs, as you move from 1250 to 1750 to 2000 degree Kelvin, you notice as the temperature goes up, you get more energy. And also another important issue, at this, suppose according to my description, at 1250 degree Kelvin is the lowest of the temperature, this is intermediate, and this is the highest of the three temperature. So at the lowest temperature of this, you see, this was the value of your lambda maxima. Now if I increase the temperature from 1250 to 1750, what I notice is this much. What I notice here, at a higher temperature, now this is the value of the lambda maxima. In the case 2, this is the value of the lambda maxima. So what you notice, the value of the lambda maxima The maximum value, lambda maxima value, you can see there, the value of the lambda maxima, it is actually going down as you are going up in the temperature scale. So in the first case that you notice here, in the first case you please notice, this is the case at the, sorry, at the highest of the three, because temperature is going up. So you see this is your maxima. Okay, you see, if you look at, if you check the values, this is the lowest of the three lambdas. Okay, three maxima. So what you notice, as the temperature is going up from 1250 to 2000, you see as the temperature grows up, what you notice is this much. As the temperature is going up, you notice here your lambda maxima is falling down. So that means high temperature means I am reaching maxima more quickly. Okay, so more temperature means value of lambda m is lesser. Okay, this is the highest one. Lambda m is the highest. If you see here, it is the highest one. This is the highest one. If I now this is the next one, and this is the farthest. This is the so you see. So that means the value of lambda m is getting lesser and lesser as I am rising the temperature. So the relationship is inverse. So now therefore we can now write down, we can now therefore write down relationship. You see in the beautiful picture I presented there, as you are rising the temperature from T1 to T2 to T2 to T4, the value of lambda m is actually diminishing. Okay, high temperature means much more lot smaller lambda m. This is actually giving a relationship. Lambda m is proportional to temperature. Okay, lambda m is proportional to temperature, as I have written here. Okay, that this is giving you lambda m is proportional to the temperature, or in other words, lambda mt is equal to constant. Now this is one of the laws of physics. Okay, this is one of the laws of physics. This is called the Wien's displacement law of black body radiation. Why displacement law? You can see here as you are going up from lambda from from the low temperature, okay, T2 to T3 to T4. What do you notice? Your lambda m was initially here. Okay, this is the value lambda m2. And as you are going up, okay, it is now becoming lambda m3. After that, lambda m4. So as you are getting the temperature up, the value of lambda m maxima is getting displaced more towards the origin, or maxima is reaching more quickly. Whatever you see is displaced towards the origin. This is displacement law. Okay, I'm talking about how the maxima is the wavelength at which the maxima is obtained is shifted against the rise in temperature. Okay, now this is the Wien's displacement law of black body radiation. So this is our first law in the journey of quantum theories. But you see, this is not again connected with the core of our quantum ideas. It is just a byproduct of the discussion. Because I have to tell you about the experiment with black body radiation, what I'm doing, in between you have got a law. Okay, called Wien's law of black body radiation, Wien's displacement law of black body radiation. Okay. Now this is when he got this law for him. So this is a Wien's displacement law. So you see, if you look at the description, I define what is a black body in practice. We have heated the black body. Radiation is okay. We have heated the black body. Okay, because of heating, the energy for every wavelength was measured, was plotted, and these wonderful graphs are obtained. By analyzing the three graphs, you can realize as the temperature is rising, okay, the reach maxima is obtained more quickly. But you know, one thing you can see, the graphs are peculiar. Next question is that, okay, fine, this still it's a very good journey so far of knowing about what is black body, what was done in experiment with black body, energy was measured, was plotted, graph was drawn, compared at various temperatures. So far it's so easy. Okay, and we get a law at the end of the discussion now in displacement law. Okay, but what do you do with the graphs? What is the problem with this experiment that you need to know? Because otherwise, so far there is no problem. Okay, then how Planck, what Planck has to do that you need to explore. Okay, but we'll do that. But we'll do that in the next lecture. Okay, this entire discussion will be continue. Okay, in the next lecture. Okay, so far today, let us be happy with when wins with this displacement law, but some good news are waiting. Okay, when Planck will come into business. So thank you. Okay. I give a bit of task to you, okay? The total energy emitted by the black body due to heating. Can you do that? You see, just get back this picture. I have heated a black body. For every energy wavelength emitted, I am measuring the energy U1, U2, U3, 4, etc. Okay? And after that, I have plotted here. My question is now, suppose I wish to know what is the total energy emitted by the black body, because it is losing a radiation means it is losing energy. So how much energy it is emitting? Okay, I give you a task for you to do at home. Okay, think about it. We'll discuss over it in the next discussion. Okay, thank you. So let us meet next day.